Hey, this is Kyone Wolf. I'm here with Betsy Kaplan in your podcast feed saying thanks for tuning in, first of all, and please keep this podcast going by calling 1-800-584-2788 or by going to wnpr.org/donate. That's the place where you become a member or you renew your membership, and most importantly, you keep us going.
And we can't do this without you. Kyone and I, along with the rest of our team, put on the Colin McEnroe Show every day of the week for you because we love to do this for you and we love the show as well. So give us a call, 1-800-584-2788, or go online at wnpr.org.
Enjoy the show.
Before we get going, this show occurs in the middle of a pledge drive. I decided the conversation was too rich and full to interrupt it with full pledge breaks. I'm just going to put you on the honor system. Please consider supporting our show. 860-584-2788. That's the number to call. You can call it any time, during the show, before, after. I guess you can't call it before the show anymore because the show's already started, or at least it's starting right now. So the way that we're going to get into this is I'm going to ask a series of 7 questions of you guys. True or false? NASA has sent an unmanned probe up to an asteroid to collect samples from an asteroid. How many people think that sounds like it might be true? How many people think how are you going to do that? It's false, can't possibly happen. All right. Not only is that happening, it's happening right now. And so there's something called OSIRIS-REx, which is up there, and it is going to take samples of an asteroid called Bennu, and we don't get them back till 2023 because everything in astronomy takes a really long time. I guess, John, what do we want to know about an asteroid? I mean, what do you want when these samples come back? What do you want to know?
No one's ever brought back a sample from an asteroid in the asteroid belt, and one of the important things about this asteroid is you should know that asteroids, most of them in the solar system, live or exist in the asteroid belt between the orbits of Mars and Jupiter. Mm-hmm. Most of them. But over time, 4.5 billion years, some of them have migrated or escaped the asteroid belt. Now, some have been ejected from the solar system, kicked out by the gravity of other planets, but some of them have been brought into lower orbits. And that's where the Earth orbits the Sun, closer to the Sun. So this asteroid is actually a near-Earth asteroid that gets close to Earth every so often. And plus, asteroids represent material that is relatively unchanged since the solar system formed. So that means if we get little pieces of it and can analyze it and share it with scientists all over the world, we have a better idea of what the solar system was like, its ingredients, when the sun and the planets formed about 4.5 billion years ago. And there's also a Japanese spacecraft orbiting another asteroid, Ryugu, that has actually penetrated the asteroid and has captured a little bit of that. And it's going to continue to do that and bring that stuff home as well. So we're really interested in asteroids because they are the rocky and metallic leftovers from the formation of the solar system. We get a piece of that, spread it around, study it. We can learn what the solar system was like when it was formed.
We now know that NASA has sent, and other countries have sent probes to asteroids and to comets. What about the sun? True or false? In the next 10 years, NASA expects to be able to send a probe that will essentially touch the sun. True? How many people think true? Okay, how many people think, nah, no way, it'll burn up? Okay, so the real answer is that it's happening tomorrow. So take it away.
So the probe is called the solar probe. It's called the Parker Solar Probe because Eugene Parker was one of these big figures who studied solar magnetic fields and how sunspots formed. And the solar probe is the first object to get very, very close to the sun. It took this long because it took a long time to develop materials which won't melt too far away. So tomorrow, I forget the time, it's going to be as close to the sun as any object has ever been. Actually, it broke that record a while ago, any man-made object that has ever been. The interesting thing about the probe is it's going to measure details of magnetic fields and The reason I'm so excited about the magnetic fields is that's the big unknown about the sun. Magnetic fields cause phenomena that affect us here on Earth. And yet we don't really know how to describe the solar magnetic field very well, except in general terms. This probe is actually going to be within the influence of the solar magnetic fields. On Earth, yes, the solar magnetic fields affect us, but we have the Earth's magnetic field to shield us from the sun's. Here, this little probe will be out there. I can't wait for the data. It's not my primary field of study, but every solar physicist in the world, we're waiting to see what happens.
Well, one thing that you said up in the dining hall was there are ways in which we know more about the very, very distant future of the sun than we do about the next 5 years of the sun. Well, first of all, do you want to jump in on that one?
No, I read the same article, and it's amazing. Yeah, we know for millions or billions of years what the sun is.
So the thing about stars is they live for fairly long. I mean, at least a star like the sun. And if you want to know what the sun is doing 5 billion years from now, it's a very, very simple set of physics that governs a star. And we know we are correct about the sun because by now we've measured other stars, so we know what the sun is going to look like, say, 5 billion years from now. But these are slow processes, and yet what affects us, 5 billion years, who bothers? I mean, what affects us are phenomena happening on the sun over timescales of years. And one of these is the so-called solar cycle, where the magnetic fields of the sun increase and decrease and increase. And as the magnetic fields increase, the number of these dark spots on the sun increase. And these dark spots appear dark because they have such concentrated magnetic fields that you don't really need gas to counteract gravity. Think of a star. A star is a constant battle between gas pressure and gravity. Pressure of the gas wants to puff up a star. Gravity wants to pull it back in. Magnetic fields act like gas pressure. So when you have a dark sunspot, you don't need gas, so it's dark. It's cooler, it's dark. Remember, hot gases have higher pressure. Cool gases, not so much. But anyway, so these are these magnetic structures, and the thing about these magnetic structures is they give rise to things called flares, because magnetic fields can combine and redistribute the energy, and the energy goes into light and X-rays, which doesn't harm us too much, but it also goes into particles, and those particles can stream towards the Earth, and they carry magnetic fields with them. If we have too many particles, they can actually disturb the Earth's magnetic field and cause geomagnetic storms. Geomagnetic storms, okay, if we didn't have any technology, we wouldn't know anything about them. The first time we felt the effects of such a large flare was in 1859 when telegraph wires started shorting. Telegraph operators got shocks because suddenly funny things were happening. And that was because of a geomagnetic storm, and that produced these effects. These days, we have GPS satellites, we have telecommunication satellites. Those are all vulnerable. And our problem is we do not yet know how to predict these events. To do this, we need to know the detailed structure of magnetic fields. Magnetic fields are hard, so there's a joke in astronomy: if you don't understand something, just blame it on magnetic fields. But if we really want to understand the effects the sun can have on us, we need those. And the Parker probe, Eugene Parker was one of the first people to explain the formation of sunspots, the cyclical formation of sunspots. Most of us were very happy that the probe was named after him. He's still alive, so he was honored while he's able to appreciate that. And so we'll get details of the magnetic field, details of other solar phenomena that happen around. And it's this, we have to live with this star, and we need to know this star well so that we can have a nice relation with it.
To put it another way, the solar flares get too bad, you might not be able to watch Game of Thrones.
Yes.
So that would be serious. That at that point we would think this is a pretty serious
On the other hand,
situation.
if the solar flares get too bad, you might be able to see aurora as far south as Hartford.
Yeah.
See what?
You might be able to see aurora as
okay,
far
yeah.
south as Hartford.
Oh, that'd be good.
So,
When we first moved to Connecticut 18 years ago, we were out about, and sure enough, we saw aurora, and I've never seen it since. But yeah, it was due to some large
Yeah,
magnetic
it was-
storm.
And that would be determined because of by the
Exactly
magnetic.
right.
Yeah, because the particles then, instead of being confined, so what happens to these solar particles is they get channeled by the magnetic fields to the magnetic poles, which are very close to the real poles, but that's where you get the normal aurora because of these particles. But if you have too many, they spill out.
The other thing I want to just quickly talk about, I mean, I do think that an awful lot of the time, most people are kind of, yeah, astronomy, that's great. Yeah, Neil deGrasse Tyson, fine. You know, and then there's this eclipse. I mean, it was, I don't think I've seen America as excited about anything since like the Beatles or something. That must be a very strange thing for you, for people who spend their whole lives or as much time as they have, watching people go nuts about this one thing.
Yeah, you're talking about the most recent solar
Yeah,
eclipse in the
yeah.
US. Yeah, so I think it was the most photographed event in human history or something like that. I mean, it passed through all of North America, so huge population centers. A lot of people were able to see at least the partial solar eclipse, and a large swath went through the country, and we were lucky enough to see the actual total solar eclipse. It was a
But what
phenomenal
was
experience.
exciting is that the normal people
Right.
were excited.
Yeah.
So
It's like a festival, yeah.
It was a festival. I watched it. So, of course, being astronomers, we organized a meeting around that. So the Solar Physics Division of the American Astronomical Society organized a meeting in Portland, Oregon, because Portland was just outside totality, so the hotels were cheap. So we bussed ourselves to Salem, Oregon. So we were at the university campus there. In Salem, the state capitol is actually next to the university campus. So the governor came out and greeted us. It was fantastic. So all the astronomers had these badges saying, "I'm a solar scientist, ask me a question." And it was, actually, we got some really good questions. And they were genuine scientific questions, and I don't think I met any science denier or anybody there. Nobody there claimed that the Earth was flat or the moon is a disk or anything. It was the best experience I've ever had.
No
in my
banging
life.
of pots and pans to scare away the moon so it would come back.
We tried that at our eclipse party, but it didn't work.
You're listening to a show that was recorded previously at Watkinson School. We're airing this show during a WNPR pledge drive, and obviously you should give some of our guests money to buy bigger telescopes, but I'm also really hoping that you're going to support public radio. And one thing that we decided was that this conversation was too fascinating and too detailed to interrupt it with actual pledge breaks with people sitting in a room. So I'm just going to ask you as we head into a break right now to call 1-800-584-2788 and make a pledge to support the Colin McEnroe Show and WNPR. And meanwhile, we're just excited to be here with this terrific panel. We're about to go to a break. Give them a little round of applause to let them know you're alive here. There's sort of it's 6 million people who think the Earth is flat. I mean, it's 6 million Americans, and I've interviewed some of them, people who actually, NPR ran a piece about a science teacher, I think in Indiana, who feels like a failure because his students think the Earth is flat, and they think that he has a spheroid Earth conspiracy theory that he's trying to market to them. And one of the reasons they think that is because several of their favorite professional basketball players, who know from spheroids, obviously, say that the Earth is flat. I mean, it's kind of astonishing in 2019 that this would be an argument that we would have to have with anybody.
Well, we've known the Earth is a sphere for more than 2,000 years. The ancient Greeks knew it. Why people in 2019 don't know it, I really don't know. But scientists are human beings. They can't keep a secret. If the Earth was flat, it would have come out.
Right.
Somebody would have written a paper.
Somebody would have written a paper. That we would wanted money to research it even further. So one of the things I ask the people, I have met a few flat earthers. So my question to them is, if you've seen the flat earth maps, Japan is on one side and the US is on the other, so I asked them to explain how Pearl Harbor was bombed. It gets to a very interesting discussion.
We'll do a question here for you guys about exoplanets. So exoplanets are basically all the planets that are not here in the solar system, right? That's exoplanets. So when I was in school, the number of confirmed existing exoplanets was 0, basically. Like, I would ask, and they would, no, forget about it. We don't know. Depending on whose numbers you accept, there's like 4,000 confirmed exoplanets, and there's like a waiting list of 3,400. I don't know. They just,
They're candidates, because you have to confirm them. They could be tiny stars, for all
Right.
you know.
I feel like they're sitting out there and they've got one of those little things that starts blinking when their table is ready or something. Okay, you can go in here. It's like, so John, you like exoplanets. You can maybe get us started on this. Here's another kind of so what question, I guess. Like, why should anybody care how many exoplanets there are, or that there are exoplanets?
Well, exoplanets is a hot topic. Students love it because the topic is barely older than them, right? So astronomy is often called the oldest science. But exoplanet and extrasolar planet research is brand new. It's just a little bit older than grad students.
Like 1990s, right around then.
1992, the first one was discovered orbiting.
But nobody quite believed that.
Right, nobody believed it because it was orbiting a dead, rapidly rotating neutron star. What? You can't have a planet orbiting a neutron star. But in 1995, in November, a paper was published by a Swiss team of astronomers that found a planet orbiting a sun-like star, a star that's similar to the sun. In fact, it was even, if you looked in the right place in the sky, it was even visible to the naked eye. It's called 51 Peg. 51 for the constellation Pegasus, the flying horse out of mythology. So that was the first planet that was found and published in 1995. Since 1995, there's been 4,000 planets confirmed by various methods and many more on the candidate list. So this is tremendous. Of course, science fiction movie writers and screenwriters and authors have known for hundreds of years that there were other planets outside the solar system. But it took science, a while to catch up. But now we know they're there, and now we're writing about these planets, right? And it's amazing. Not only do we know there's 4,000 other planets in about 3,000 other solar systems, which, if you do the arithmetic, some of those systems have more than one planet, just like we do. So that means we're starting to characterize those systems. What do I mean by that? We can tell with a reasonable amount of accuracy. We're getting better at this, but we've only been doing it for a few years. We can tell if a planet has an atmosphere, and if it's a good night, we can even tell you some of the atmospheric constituents that that planet has. Now, that is, I can't tell you what I'm really thinking, but it's really amazing that we can do that, in some cases from Earth, but in some cases from orbiting satellites that their view of the cosmos isn't obscured by the Earth's atmosphere, which is a real pain for astronomers. It's great for breathing, but it's terrible to look through. No two ways about it. But when we use instruments like the Hubble Space Telescope to look at exoplanets, which, by the way, wasn't designed to do that, but it's really good at it, it shows us perfect evidence that these planets exist. We can tell how big they are using one method. We can tell how massive they are using another method. And from combining those two methods of detecting planets, we can calculate the density of a planet. Is it a gas giant planet like Uranus, Neptune, Saturn, and Jupiter? Or is it a rocky planet like Earth, Mars, Venus, or Mercury?
Right.
We can tell that about certain systems. That's why it's so exciting.
You can also gauge how hot it would be or how cold it would be, right? Depending on how far it's from the host sun, you can gauge the temperature range.
But you have to understand the star first.
Right.
Yeah.
So we have to consult with our stellar experts so we can help characterize that system.
Right. And from the chemical composition, you can gauge maybe if they have the proper chemicals that it would be a signature of life.
That's a big thing now. What are the biosignatures? So think of it this way. If we were many, many light years away from the solar system, how would we know that there's life on Earth? And that's not an easy question because you might think oxygen, but hey, there are other ways to produce oxygen, as people figured out. So what chemical signature would you think is unique to life? So that's a problem. But to me, the big interesting thing about exoplanets is what exoplanetary systems have shown us. We used to think we know how the solar system was formed. All our scenarios have gone out of the way because we can't explain most of the other exoplanetary system if we say this is how a planetary system is formed to explain the solar system. So there's such interesting physical processes that are going on that we don't quite understand yet. And the other, to me, astonishing thing is, like, we found the Kepler spacecraft was meant to discover these planets, and we found a multiplanetary system around a star which is 11 billion years old. That means that star was as old as the sun is today when the sun was formed. So we don't think any of those planets are sort of Earth-like, but I mean, we have some characteristics, but think of it, if life were formed on those planets and they managed not to kill themselves, they became intelligent and managed not to kill themselves, they would be ancient. So the question is, are they going to be wise? Or are they going to be stupid? Old age can do both.
It's true. You were going to say something?
Yeah, going back to this discovery of the planets, this is something, again, that the average person can do. There's so much data out there that they have a hard time going through it all. And I think it's called Zooniverse. There's a website called zooniverse.org.
And Planet Hunters.
Planet Hunters, have they moved over to TESS yet? Because the Kepler part is sort of done.
Right. But Planet Hunters they're making Tesla data available very quickly now.
Okay,
so if you go on one of those sites, what do you?
Yes, so you're presented with some graphical data, and you just visually say, yeah, there's a signal here, right? And you say, yep, I think there's a planet there, and they'll run it through their model and say, you know what, you're right, there's a signal there for planet. So you could discover
and
an
if you're right,
yeah,
you get credit when the paper is written.
Published, yes.
As a co-discoverer.
Yes.
You do, yes.
So,
it's happened. Yeah. It's happened.
Yeah.
I would have guessed planet, not in our solar system. No way you can see it like through one of your telescopes.
Well, through our telescopes.
No, that's true. I mean, we've only directly imaged very, very few planets. We have a few, but no, these are all.
He said naked eye. You said naked eye for one of them, right?
No. The star is
the
naked.
star.
Eye.
The star. Okay.
Yeah, star is naked eye.
Yeah, that wasn't working for me.
Yeah.
So okay, I get it.
And I'm talking going through the Kepler data or the test data, or whatever, right? So.
But we can discover them like Kepler discovered most of, and what TESS is doing now. When a planet goes in front of a star, the starlight dims. It dims in a very predictable way. So you look for these dimmings. And how much the starlight dims depends on how big the planet is compared to the star. So that's how most of the planets have been discovered. The first planets, though, were discovered by a very different method, where you look at the starlight and see if the star is moving slightly. Very slightly, because that's where, we learn Newton's laws in school, Newton's third law. For every action, there's an equal and opposite reaction. When you have a planet going around a star, technically the star is also going around the planet. So the star moves because of the planet. So you see the motion of the star and deduce there has to be a planet there. As it happens, because you need a heavy planet to move a star, stars are heavy, the first planets that were discovered were very close to the star, because then the gravity would be higher, and they were humongous. They were what we called, because they're close to the star, they're hot, and they were basically Jupiter-sized. So these are hot Jupiters. Hot Jupiters in orbits that are a few days. So you would age very quickly, you know. You'd have a birthday every 4 days, every 5 days.
But we like those because they're easy for students to detect.
Yes.
Every 4 days
Yeah.
they transit. Hopefully it'll be at night, but so it's really interesting.
It's fun. And it's very simple high school physics that allows you to do it. That's the nice part about it.
I don't know what they meant by this, but before we actually got to the formal part of this, and I'm just saying this because I see some young people out there and parents of young people, they were saying these days the money is in exoplanets. So if you're going to choose an astronomy career,
He's taking us out of context.
you know, and you're thinking helioseismology or exoplanets, apparently do the exoplanets. It's like plastics in the graduate. It's like, do that, you know.
But the younger people won't get that reference.
No, they won't. So here's a true or false. Astronomers have found a way to take a photograph of a black hole. True? It's sort of a trick question, as it turns out, because next week, right? A week from today? Is it a week from today? Yeah.
10th.
Yeah.
Black holes, do you know what black holes are? Or we can save a lot of time. You saw the movie, right? Either the movie Black Hole, made by Disney, if you can believe that, or Interstellar. So a black hole is a place in space where a star used to be, but the only thing left is its gravity. And it doesn't happen to small, low-mass stars like the Sun and most of the stars in the galaxy. Most of the stars in most galaxies are small, dim, and not very massive, but they live a long time. Black holes are the kind of an endpoint for massive stars. And it's just that. It's a place in space where there's a point of infinite density where a star used to be. And the only thing left of the star is its gravity. And the gravity is so powerful, so strong, that light cannot escape from the surface of this black hole. So that's what a black hole is. So black holes all by themselves in space are invisible. Gravity caused that. There's almost no way you can see a black hole that's all by itself. But luckily, sometimes, one thing leads to another in these conversations, Colin. Most stars in the sky are not single stars like the sun. They're a part of multiple star systems, a double star, a triple star, even quadruple stars. So there are a lot of binary stars in the universe, in our galaxy. And sometimes black holes form in one of these binary systems. And if things are just right, or just wrong, I guess, the black hole can draw material from its evolved companion star, and that material swirls into a flattening disk of gas that's siphoned away from the companion star as the two objects orbit a common center of gravity. This gas gets so hot that it gives off X-rays and ultraviolet light. They're very bright sources of X radiation. But what we see is a star that's moving really, really fast about something that we can't see. Now, we can measure the mass of the system and determine where the center of mass is, and we can calculate the mass that has to be present to make the star do that, as long as we know the mass of that star, which some experts can help us with. So that is kind of a backdoor approach of photographing a black hole. It's not the black hole itself, really, but it's the material just before it falls into the black hole. It's really hot. It's a bright source of X-rays, and that we can image, photograph.
And there'll be a press release next Wednesday about the new discovery from a new telescope called the Event Horizon Telescope. So the event horizon of a black hole is sort of the closest you can get to a black hole without being swallowed by it forever. So the Event Horizon Telescope, apparently they have some interesting results, and we're all waiting to see. And they're apparently spectacular enough that the head of the NSF is actually going to be there at the press conference.
Nice, very nice.
So, and I would just like to add one thing to the black hole stuff. You can also get gigantic black holes, and they exist in the centers of galaxies. So black hole comes in two flavors. There are these stellar mass black holes, and then there are what we call the supermassive black holes. By what I mean my friends who study these. They call them supermassive black holes because they can be 1,000,000 times as heavy as the sun. And the supermassive black holes are, and the disks around them that produce X-rays and stuff, those actually are what you would call quasars and active galactic nuclei. So quasars are nothing but these humongous black holes sitting at the center of galaxies with things falling into them. So it's the same phenomenon, but at two different scales.
And correct me if I'm wrong, the Event Horizon Telescope isn't one single telescope. They've actually linked
I believe so, yes.
linked telescopes
yes.
across the Earth
Yeah.
because it's the size of a single star,
Yes.
and it's at the center of the galaxy, which is tens of thousands of light years away. So you're looking at this tiny, tiny thing. So they've expanded this virtual size of the telescope by
Yep.
connecting these far-flung telescopes
Yeah.
together.
And the thing about a black hole is the region around a black hole, what you see is very non-intuitive. So if you fell through a black hole, you wouldn't see anything different. But if your friend were still outside the black hole, you would be sort of frozen along the event horizon. And depending on how you're moving, the shape that you see would be different depending on which angle you're looking at. So the simulations of what we could see around a black hole from event horizon were almost as exciting as real things. So we want to see, what do they see?
Yeah. I want to first of all confirm what he was saying too. My understanding is that this is a telescope, essentially what they call a virtual telescope,
Yeah.
essentially the size of the Earth.
Yes.
In order to do this. I also want to say that in the course of my research into this part of it, I discovered there's like several different parts of a black hole, including, and this is my favorite term of the week, there's one part called relativistic jets, which I feel like is like 1990s New York street gang, you know? It's like...
Boy, are they fast.
Yeah. When you're a jet, or possibly you might not be, actually. So, we're all reading French deconstructionists. Okay, we're about to take a little break here. It's a pledge drive for WNPR. Support astronomy, obviously, and also Dave needs some money to buy a new telescope too. So, but also support public radio. It's the only way that it really happens. So we decided that this show is so special. We did not want to put in any pledge breaks or anything like that. So I'm just going to trust people who are listening right now to go to the phones, call 1-800-584-2788, make a pledge what you can. There's people answering the phones. And meanwhile, a round of applause for this terrific panel. We're going to take a break. We'll come back. We'll be back, we promise, right after this.
Hey, it's Kyone Wolf here with Betsy Kaplan, taking a second out of your podcast. I know you thought you were totally off the hook from listening to the live fundraising, but we just want to take a second to say thanks for tuning in. And also, please help us keep this coming into your podcast feed. The number to call to be a member or renew your membership is 1-800-584-2788 or WNPR.org/donate.
And you have lots of advantages listening to the show on podcast because we're only going to speak to you for about 20 seconds, maybe 50 seconds, unlike 5 minutes. So reward us with the fact that we're speaking to you less time. We're taking less time out of your enjoyment of this great show that you're listening to. Give us some support to keep these shows going, no matter how you listen to them. 1-800-584-2788 or go online at WNPR.org.
I think it might be a good time, Jenny, do you think, maybe to go to the audience? And I have lots of other questions, but I think it's also, they probably have more imaginative questions than I do.
I'm wondering about funding for the equipment you use. I'm not talking about the satellites per se. That's obviously government-sponsored, I guess, less the guy who owns Tesla. But let's say these huge telescopes and things, is that governments for the most part, maybe universities, and also the technology? And do you go to, as an astronomer, go and say, gee, I want to know how to be able to do this. Can you figure out how to make something that I can do that? Or is that changing rapidly or not?
So in the US, historically, most of astronomy have been privately funded. By most of astronomy, I mean not the space-based ones, but the ground-based ones, the big telescopes. In Europe, it always has been government funding, and that's also the model in most other countries. So US has been strange, and so it's the Carnegie Institution and Harvard, which at some point were the only places where you could really do professional astronomy. Then, which is why in the I think 1950-something, I should know the date because I'm a part of that organization, a group of universities decided they need to lobby the government to form national facilities. So that's when the government put in some money and formed the National Astronomical Observatories, NOAO, and those are basically, you compete for time. Caltech, for example, owns a lot of its own privately held large telescopes. They have currently the biggest ones in the world, the 10-meter class Keck. There are other 10-meter telescopes, but they're European. And the US model has been a bit problematic because Europe is going to build a 30-meter sized telescope. That's humongous.
100 feet.
Yes. And in the US, there are two different consortia trying to build two of these. And as a result, both of them have financial problems. So we're actually, this organization I told you about, the Association of Universities for Research in Astronomy, they are trying to bring the two groups together to see, and these are private, so people who don't belong to the consortium can't get any data from these telescopes. So they're trying to see if they can persuade the government to put in some money in both of these so that any old astronomer in the US can get some time. So yes, it's a bit complicated in that sense.
And very competitive.
Very, very competitive.
If you want to study something and you need a big telescope because what you're studying is far and faint, which applies to a lot of different celestial objects, you apply for telescope time. And the telescope allocation committee, right, TAC, Telescope Allocation Committee, gets all the proposals every semester and looks at them, and many of them make it, but most of them don't, and they reapply for next time. So it's very nerve-wracking, and it's exhausting to write telescope proposals, and there aren't
too many.
There aren't very many big telescopes, and the more we build, that's one of the things we were talking about earlier. When people fund, are interested in science and fund observatories to be built, I bequeath the university $1 million to build this observatory. very little thought is given to, once the establishment is built and working, how to keep it working, how to pay the people that can keep up the equipment and the cost to keep the equipment running. A telescope is like a car. Your brakes wear out because you use them. The gears wear out in telescope drives. They have to track the stars as the Earth rotates. When you point a telescope at an object in the sky, if you don't have a precise mechanism to carry that 100-ton piece of glass and track the star compensating for the Earth's rotation, you have to constantly adjust the position of the telescope. If you've ever gone to a star party, that's kind of a pain in the neck. And you can't take 10-hour-long exposures of a distant galaxy, move it a little bit to the left. It just doesn't work. So funding an observatory is more than just building it the best, baddest telescope in the world. It's keeping it running for a considerable amount of time. That's the hard thing.
Yeah, Dave?
It does seem to be the heyday of observational astronomy, though. I mean, back when I was a kid, many years ago, the size limit was about 200 inches. The Hale telescope was about it. And it was because basically the Earth's atmosphere distorted the image beyond that. You could magnify it more, but you just get a blurrier image. But with active optics, AO, you can actually tweak the mirror to compensate for the movement of the Earth's atmosphere, and then the sky's wide open. These monster telescopes, like you said, 30-meter telescopes are being
Yeah,
designed.
the monster telescopes are not all of them have active optics at the top, but sometimes the size of the telescope is a light bucket. What actually allows you to study the object is the sophistication of the instruments. Like the Palomar telescopes are nearly, 100 years old now? But we can still use them because the instruments have changed.
Right.
The telescope itself is nothing, just a bucket to collect light. I think I saw a question.
Yeah, although I wanted to ask you one question too, Dave. As an amateur, but a very passionate and sophisticated amateur, what's the best telescope you have access to? Like, if you want to look through something better than what you own, what can you do?
I own. So Yale has a lovely observatory and planetarium open to the public on Tuesday nights, and they have a 16-inch.
That was a commercial.
Yeah. I very good.
I didn't do that.
They have a lovely 16-inch reflector there on site, and except for its location in downtown New Haven, it's a beautiful instrument to work on. But there are places you can actually rent time on these other sites. So it's neat how these larger telescopes are commissioned for professional astronomers. The smaller ones are being decommissioned, and the access to amateurs is available. And if you've got enough money, you can rent time on these. Yeah, sure. And the technology too. This advanced optics where you can actually tweak the mirror, that's coming down so that amateurs can actually afford to buy their own systems to do that.
Though, I mean, I must say that professional astronomers rarely go to the mountains these days.
I feel as though there's some conversations with your wife about this that you've had. Like, no, Dave, you can't.
I was hoping she wasn't here, so he would speak freely.
Yeah.
It is like owning a boat. You know, it's just a place to shovel money.
All right, more questions. Where's Jenny? Where are you? Okay, you're there. Okay.
So I was wondering to what extent, if at all, in any of your work, you cross over or are involved with the assessment of extraterrestrial life.
Oh yeah. We're visited all the time. That's how we get our funding. No, aliens don't exist. No. Thank you. So I get questions like that all the time. Right? And most scientists, and I went to a wedding with Deborah Fisher. My wife and I were invited to a student's wedding. She used to be the former department chair at Yale. And we had a great conversation with her. She said, deep down, even if they're not astronomers, even if they're like chemists or geologists, everybody wants to know if there's any other life out there.
Yeah.
And we know that's true, right? But we need some proof. Give me a transistor from an alien spaceship, maybe a phaser or a transporter, or even a food synthesizer would be great. So the famous astronomer Carl Sagan was famous for saying lots of different things, but one of the things he said was, if you're going to make these extraordinary claims,
You need extraordinary proof.
you need this extraordinary evidence. And so far, the evidence is not extraordinary or compelling. You might say, well, I studied statistics when I was in college, and with all the stars and planets out there, there simply has to be life.
Yeah.
We would agree.
Yeah.
But are we 100% sure? Well, we're never 100% sure in science. And most of the time, that's okay. Because science is a process from not knowing anything about something to knowing more and more and more. That's why you're never done. We've only been looking for extraterrestrial life for 60 years. Now, in comparison to how old civilization is, that's really not very long. And we're really not very good at it. But we're not stupid, we're pretty intelligent, and we're making progress, but the universe is big. And it's really deep. So we haven't found any of this compelling evidence yet, but no one's really giving up.
The other thing to consider too is that our one example, the Earth, right, our data point of one, most of the life and most of the time that life has been on the Earth, it's been slime.
Yeah.
Mm-hmm.
So, I mean, when you think of intelligent or life in the universe, if they're thinking little green men, you can have a conversation with
Little green
people. Okay.
Person.
Creature. I don't think there'll be anything like us.
But you know, the realistic thing is, if there is life out there, it's probably going to be green slime.
Yeah, and hence my earlier comment about biosignatures, because green slime is not going to transmit messages.
Right.
So we need to know what is it that they exude, that they contaminate their atmospheres with, so that we can know that there's life there, that these are life processes. And I'm a big science fiction fan, and I'm a classic science fiction fan, so people like Larry Niven and all those. So there's the series by Niven called Draco's Tavern, which is a tavern where all sorts of extraterrestrial intelligent beings come and drink. And they're nothing like us. Their life systems are completely different. And I'm more inclined to think that the universe, being what it is, the strange place that it is, we might not be able to recognize life. Mm-hmm. Because we, like the proverbial drunk, we are looking for keys in the light. We're looking for life like our own. The biology, the chemistry of life like our own. Maybe it's not. I'll be very disappointed if it is, frankly.
On a couple of occasions, I've interviewed Paul Davies, who I think he's sort of like one of the people they call, or at one point he was like maybe the person who had to call the president or something. And one point that he made is, we haven't really classified all life on Earth yet, you know? And tomorrow they're going to find some kind of extremophile living by an ocean vent in some impossible thing that's able to withstand temperatures that should kill it. Like we don't know everything here on Earth, and we're like upset that we don't know. I mean, that quest. I mean, think about how vast the cosmos really are.
But learning about those extremophiles,
right,
those
might
organisms,
actually help us.
Yeah.
right? So in the last 50 years, different sciences have been learning things. Astronomers and planetary scientists have been learning that there's water everywhere. There's organic compounds everywhere. Mm-hmm. The Saturn system is full of complex organic molecules, mm-hmm, right? Which is what life on Earth is based on, right? And we find amino acids that fall to Earth in meteorites, okay? So we know some of the same processes that took place on Earth have taken place elsewhere. Now, there's no little creepy crawly things inside the meteorites, right? Mm-hmm. But we also know that we can spontaneously produce these amino acids in a laboratory in a dank basement university lab in Chicago, like they did in 1950, and after a week, out comes a vial full of slime with 5 different amino acids, and 20 years after they did that initial study, cleaning out that lab, they found a refrigerator with some of the same material left over from the original 1950 experiment. With new technology, 22 amino acids were found in that sample. that spontaneously was formed in this innocuous experiment conducted by a mentor and his grad student. So we know the processes, we know the chemistry of life, at least one possibility for that. But somewhere else, there is a different environment. Whatever is growing up there, in whatever liquid is there, has a whole different planetary evolutionary path. And it could be an entirely different chemistry. And they're probably laughing at us right now, right?
If they knew of our existence, they might be having the same debate.
Right. Although they totally didn't get the joke about the drunk looking for the keys. So you'll have to explain that to them eventually. So that's where we're going to end the show. I once again want to thank my guests, Dave Noble, the passionate amateur astronomer, Sarbani Basu, the chair of Yale's Department of Astronomy, and the Sky Guy from the University of New Hampshire, John S. Gianforti. And let me once again just say, it's Pledge Drive. I really do need you. We didn't want to interrupt this with any pledge breaks, but now I need you to pick up the phone, call 1-800-584-2788, or give online at WNPR.org. You can find a little Donate Now button. Thank you for doing that. It makes things like this possible.